Hi and welcome to another of BYJU'S FB Live. Today we are discussing physics. Today we are discussing magnetism. Okay. Now you must have gone through electrostatics, electrocurrent, capacitors. I'm assuming that, and then having a short discussion on magnetism when you have already into the chapter of magnetism, or you're about to go into the chapter of magnetism, or you have recently done the chapter of magnetism. This discussion would be helpful. All right. Now the first thing you realize once you start studying magnetism in 12th standard is that it has very less to do with actual magnets, right? Because the very first thing we learn is that the property of magnetism has its sort of say the fundamental source or the real cause hidden in charges itself. So we've been learning about charges in electrostatics and we have been learning about charges in electrocurrent, and in magnetism as well we'd only be learning about charges but something added to the charges, right? So now what happens is there are certain properties of charges which come up when you observe them while moving, okay, and that's what constitutes this chapter of magnetism. Now this chapter of magnetism is basically divided into two parts, okay. In fact, electrostatics was also divided into two parts. There we studied about how electric field is formed, and then we also studied, which was a small part, about how this electric field applies force and all the analysis of force. Now here also we are going to learn about what is magnetic force and how does magnetic force manifest itself and what are the formulae and how to deal with it. And then there's magnetic field, right? From where does the magnetic field arise and how does it arise and all those things, right? So basically two parts, force and field. So let's start with force. So now what happens in this part, I'll be telling you that there's a magnetic field already given to you, okay. A magnetic field is like an electric field, very similar, except there are a few properties which are different, but it's basically a field, okay. It's a vector field, and like in electric field you had E, in magnetic field you're represented by a vector B. Now what happens if you have charge in a magnetic field, right? If a charge is just placed in a magnetic field at rest, then you find then that the charge experiences no force. That a charge in rest in a uniform magnetic field, a magnetic field which is not changing with time or space, doesn't do anything to a charge. A charge just stays there, okay. Another fascinating thing is, if you start moving this charge along the direction of the magnetic field, nothing happens, okay. But when you start moving this charge in this magnetic field such that it bears an angle with the magnetic field, then you find that there is a magnetic force. And the interesting thing about this magnetic force is that it is always perpendicular to the velocity, okay, always perpendicular to the velocity. Because of this reason, magnetic force can never do any work. Now there's a formula for finding the magnetic force on a charge with a charge q moving with a velocity v and given the magnetic field is b. But for that we need to know about cross products. Now cross products is at the heart of this chapter. You need to really learn how to find cross products. Now what is a cross product? A cross product is basically a multiplication between two vectors, right? There are different kinds of multiplication between two vectors, right? Scalars can only be multiplied in one way, vectors can be multiplied in many different ways depending on how we define that multiplication. There's a dot product, there's a cross product, there's a box product, and all kinds of products. We have to learn about dot and cross. Here will be in this chapter we focus only on cross product because that's what we need. Now what's cross product? So you have a vector A cross vector B. Now cross always gives you as a result a vector. Dot always gives you as a result a scalar. A dot B is a scalar, A cross B is a vector, okay. Now if it is a vector, the first question arises, what is the direction of this vector? Magnitude is easy, okay. So I have these two pen here. Now this is a pen which is pointing that way, this is a pen which is pointing that way, right? So let's say these two represent my vectors. This is my vector A, this is my vector B. So the blue one is A and black one is B, okay. So vector A, vector B. If I have to find A cross B, okay, then what I do is I use my right hand all the time. Okay, it is called right hand rule. So I stretch the fingers of my right hand towards this vector A and curl it towards B, and the thumb gives me the direction of the cross product, which is inside the screen in which you are watching me. So A cross B is inside. Okay, and I deliberately put my hand like this. I could have put my hand like this as well, but in that case I wouldn't be able to flip it towards B. Okay, so see that the idea is that you have to put your hand in such a way that you can curl it towards the other vector. So A cross B is inside, but if I ask you B cross A, so B cross A is outside. Okay, I can't do this because I can't, for B cross A I can't put my hand like this because I won't be able to curl it towards it. So B cross A is outside. Okay, and not just outside, it is perpendicular to both A and B. So A cross B or B cross A is perpendicular to both the vectors. In fact, the plane which these two vectors make, that vector will be perpendicular to that plane. Okay, this is very important to understand. All right, so that is cross product. Now what happens in for a force on a charge, magnetic force on a charge, that force is equal to Q, which is the charge, magnitude of the charge, times V cross B, V vector cross B vector. Okay, so let's say there's a charge here, and this is your magnetic field. Okay, and this is your velocity of the charge. So there's a charge here which is moving in that direction, but this is the magnetic field. Let's for simplicity take a uniform magnetic field. Okay, now the formula says Q into V cross B. So which one is V? This is V, this is B. So V cross B gives me a direction which is outside the plane, so outside the screen. So the direction of the magnetic field, I don't have a pen here, but imagine the direction of the magnetic force will be outside. So this charge would be experiencing a force in the outward direction like that in this moment, because once it experiences a force in that direction, its velocity might change. The velocity will change, right? The speed will not change because the force is always acting perpendicular to the velocity. Because you see F is equal to Q into V cross B. V cross B is always a vector perpendicular to both V and B. So magnetic force is something which is always going to act perpendicular to the magnetic field as well as to the velocity. And if a force is always perpendicular to a velocity, then it can never do work on it. Okay, because F dot V will be 0 and V is ds by dt, so F dot D or displacement will also be 0, right? So it can never do any work, and that's the reason why a charge can never increase its kinetic energy whenever it is in a magnetic field, just a magnetic field, right? Now what happens, there are certain interesting cases come when you have velocity and the magnetic field perpendicular to each other. Okay, this is something you must have done in your classroom, or you're going to do in your classroom. Now this is my magnetic field, this is my velocity. So the charge is going this way in this moment, and this is my magnetic field. Now when you do this, by the way, I think I should also tell you that if you do A cross B, you know how to find the direction. The magnitude is just AB sine theta, theta being the angle between A and B. I hope you know that, because it's something we learn in 11th standard already, right? So when I do Q times V cross B, this is Q V B sine theta times, this is the magnitude, into that unit vector in that direction, right? Because that unit vector always is used to get to know a direction. That's all. Now if this is the magnetic field, this is the velocity, then what happens? Okay, so first thing, V cross B will be in the outward direction. It means the force will act in the outward direction, right, to this charge. Now the magnitude of that force will be QVB sine theta. Theta here is 90 degrees, so it will be QVB. So QVB force acts perpendicular, that is this way, but it is always perpendicular, because of which what happens, this particle goes into a circle. Okay, now what kind of circle will it move into? This circle or any other circle? So the simple way to understand in which plane the circle lies is to understand that this initial velocity with which the particle is moving would act as a tangent to that circle. So I see that this is the velocity, so the circle will be this circle, such that this velocity is a tangent. So this particle would continue to move like this. Yeah, I want to come back. All right, so that's what it does. Now you are asked to find the radius of this thing. So the simple idea behind finding the radius or the time period or blah 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 is to understand that this magnetic force is what provides you the centripetal force. Okay, so mv square by r, the formula for the centripetal force, you know that mv square by r will be equal to the magnetic force which is acting, which is qvb. Vb gets cancelled, you find that r is equal to mv by qb. Okay, mv by qb. So in the same magnetic field with the same charge, if you had if you compare two charges with the same charge magnitude, same magnetic field, one with higher velocity, it will undergo a circle with a greater radius. All right. Similarly, when you find the time period comes out to be 2 pi m by qb. Okay. So time period is independent of the initial velocity. So if the magnetic field is same, charge is same, no matter how fast the particle is moving, and if the particle is moving faster, it will cover a bigger circle, but they will both have the same time period. So let's say, imagine that two particles here, one has higher velocity, one has lower velocity, same magnetic field, same charge. Then what will happen when you leave them, or when you allow the time to pass, then what happens, this goes to a bigger circle, this goes to a smaller circle, but they reach back to the same point in the same time. So time period is same. All right. Now this is one kind of thing which you see in magnetism. The other kind of thing which you see is when the magnetic field is not perpendicular to velocity. So you know, right, that all this that we were discussing was when it was perpendicular, theta was 90. So when it is not perpendicular, then what happens? Okay, so here is my velocity again, here is my magnetic field again, and this time they are not perpendicular, they have an angle. Let's say that angle is whatever, let's call it theta. Okay, this angle is theta, this is the velocity, this is the magnetic field. Now what happens now? What will I do? I'm going to resolve this velocity, okay, or I can resolve the magnetic field as well, but resolving velocity is easier in the direction of the magnetic field, okay, and perpendicular to the magnetic field. So for simplicity, let's take it this way. Okay, so this is my magnetic field, this is my velocity. So in the direction of magnetic field and perpendicular to the direction of magnetic field, I would simply resolve the velocity. So this perpendicular component is what is creating the circle, the circular path, and the horizontal component of the velocity is not going to change because there is no force in the direction of magnetic field, something I had already told you. And you already also know that V cross B is VB sine theta. Theta 0 means no force, right? So this component experiences no force. So this component is going to remain the same. So if this is theta, V cos theta is not going to change. Only V sine theta is the one responsible for creating the circle. So in this case, the radius of the circle will be not mv by qb, but mv sine theta by qb, because sine theta is the perpendicular element. So this will create a circle, but at the same time it has a horizontal velocity, because of which it will also be moving forward. So this guy will start on a circle, but it is also moving forward. So it'll go something like this, you know, like it is traversing on a spring, or you know, like this. This is called a helical path. It will move in a helix. Okay, so helical path is very simple. Once you have resolved the velocity, the radius of the helical path is mv sine theta by qb. Time period is still same because time period is independent of the initial velocity, 2 pi m by qb. Now a new thing comes, pitch. What is pitch? In one time period, how much does this particle move forward? One time period means from here it starts, one circle it completes. In that completing one circle, how much forward it has gone, right? That is called pitch. So you know that it takes how much time to complete one circle? 2 pi m by qb. That is the time period. And what is the horizontal velocity? V cos theta. Time period and velocity, you know, velocity into time will give you the distance. That's the pitch. That's the pitch formula. V cos theta into time period, which is 2 pi m by qb. So 2 pi m V cos theta by qb will give you the pitch. All right. So you get all sorts of questions just on this idea. Okay. And the chapter of magnetic force is actually not a very big chapter. The concepts are really small. Okay. It's just that it's such a nice visual kind of a chapter that they can give you different kinds of problem. I mean, the particle was here, this is the magnetic field, and this is the velocity. It is moving in this fashion. Where will it be after 5 seconds? Where will it be after this many seconds? Then you have to know that how many circles would it have completed, what would be its pitch, what would be its location. So all kinds of questions you can solve using this idea. But remember, this is the first part of magnetism, where magnetic field is already given, and you are supposed to find the force. Now we come to the second part of magnetism, which is which doesn't have such beautiful helices and all that. Okay, so magnetic field. Okay, so now to understand magnetic field, if a charge is just kept somewhere in some place, it creates around it an electric field. You all know that kq1 q2 kq by r square. Does it create a magnetic field around it? No. Okay, but if a charge is moving with a constant velocity, it creates a magnetic field around it. Okay, so a charge at rest does not create a magnetic field. A charge moving at constant velocity creates a magnetic field. What happens with a charge that is accelerating? So if a charge is accelerating, it creates electric field as well as magnetic field, as well as it gives off electromagnetic radiations, EM waves, light. Something will going to you'll see in after I think a couple of chapters, where does light arise and all that. Light is an electromagnetic wave, and it you know, whenever a charge accelerates and blah blah. Now, all right, so we are not going to be concerned about charges accelerating. That's a good part. We are just going to be concerned about charges moving at constant speed. Okay, now I've got a charge which is moving at this very moment. Its instantaneous speed, the instantaneous velocity is v. Okay, so this is a charge. Imagine a charge over here. That is the velocity v. At this very moment, I have freeze time. Okay, now I want to analyze, at this moment it has this much velocity, what magnetic field is it creating? Now magnetic field, first of all, understand, is a property of space, like electric field. So you have to specify where magnetic field. Right, so I have to tell you, okay, at this point, to tell me this point what is the magnetic field. Now what will I do? What I do is, first of all, from this charge at this point, I draw a vector there. I call it r, the location of that point. Okay, r vector. Now what happens? That magnetic field is given as a formula, simple, mu naught by 4 pi q into v cross r by r cube. V is the velocity vector, cross r, right, divided by r cube. So r, it is actually an r square law, again, like electric field, but you have an r on the top, so that r, the magnitude of r on the top and the magnitude of r on the bottom gets cancelled. This is something your teacher will tell you definitely. Anyway, so this is my v, this is my r. Okay, so I have to do v cross r. V cross r, that is the direction. That direction means at this point the magnetic field is in that direction. Okay, I don't know if you can see that. It is in that direction, and its magnitude is I VR sine theta, the angle between V and R, divided by R cube. So R gets cancelled, you get in the denominator R square. So this is the fundamental formula for finding magnetic field. Now you have then Biot-Savart's law, Biot-Savart law, whatever you want to call it, names don't matter, which tells you how a magnetic field is created by current. Because when you have a current carrying wire, is nothing but a bunch of moving electrons which have an average velocity in the forward direction, right? Because they have an average velocity in the forward direction, they create a magnetic field around them, right? So that formula you learn as mu naught by 4 pi I into dl cross r by r cube, where dl is a small vector in the I direction. Okay, and then you go on to learn a lot of things. You learn what a solenoid is, in which a current is flowing. Inside a solenoid, the magnetic field is mu naught Ni if it's an infinite solenoid. If in the semi-infinite solenoid, it is mu naught Ni by 2. Then there's a loop. In electrostatics, you used to have this loop, right, of charge. The electric field at any point on the axis, the electric field used to be kqx upon 4 pi epsilon naught r square plus x square whole to the power of 3 by 2, if I remember correctly. There was an effector of x in the numerator as well. Okay, so now the magnetic field on a current carrying loop, this is not a charged loop, current carrying loop, a loop which is carrying current in it, and we're talking about magnetic field on the axis. What will be the magnetic field? That there's a formula which is mu naught I r square divided by 2 r square plus x square whole to the power 3 by 2. It is always good to remember these formulas because you won't have time to derive it in your examination. Now the interesting thing is the magnetic field in this axis, okay, if you find it this, so the way you find for a loop the magnetic field is you curl your fingers along the loop and the thumb gives you the direction of magnetic field. So this is a second form of the cross product rule which we have derived for looping things. it becomes easier. So if you have a loop and current is going like this, I just loop my fingers like this, thumb gives me the direction of magnetic field. So this side of the loop also, this is the direction of magnetic field, this side of the loop also, this is the direction of magnetic field. So the magnetic field direction is always this way. The loop is going like this, the current is going like this. But remember, in electric field, electrostatics, when you had charge over a loop, in that case what happened, the electric field here was this way, here was this way, opposite, okay, or this way, depending on what the charge is. Let's say the charge was positive, so it was like this. But if there's a current carrying loop, then the magnetic field is always in the same direction, mu naught I r square by 2 r square plus x square whole to the power 3 by 2. That's the formula. And then you also learn the magnetic field to an arc at the point, and again you use the modified, I call it the modified cross rule. And then you learn motional EMF, where there's just a conductor which is moving and all those things. But motional EMF they teach you after the electromagnetic induction, so not to be discussed now, we'll discuss that later. So this is basically the overview of the chapter of magnetism. Now magnetism is a fairly decently new chapter to you, and it is also a very interesting chapter, okay, because these ideas are like very fascinating. See, only a moving charge creates a magnetic field, and only a moving charge experiences a magnetic field, okay. And we found out that magnetism, magnetic fields are coming basically from charges, from where electric field is also comes, and from there we were able to deduce the relationship between the electric field and the magnetic field. We realized that they are like sort of the same thing, the two sides of the same coin, okay. And we coined a name called electromagnetic force, say, which signifies both these forces joined together once we understood from where they come. Now how does magnets work? Now magnets don't have current. You don't know that. Of course you feel, you have touched a magnet, you never feel a current, there's no current flowing in it. Then how does a magnet create magnetic field? So there's something called domains. So there's like kingdoms inside a magnet, you can imagine, and each kingdom has, so because you have an atom, right, an atom has an electron going this way, round and round and round. So it's like an atom itself carries a current carrying wire, because there's a charge which is moving all around the nucleus, right? So isn't it like a current carrying wire? So an atom has a magnetic field, okay, a magnetic moment we call it. So now an atom has a magnetic moment, and many atoms which have magnetic moments in the same direction bunched up together, like say a lot of atoms have magnetic field in that direction, or magnetic moment in that direction, which is, magnetic moment is just a fancy word for, if you have a loop, you take the current in that loop and then you multiply it with the vector A, and basically multiply I to the vector A. A is the area vector which you get when you loop your hands in the direction of the current, okay. It's just I into the area, and there's a direction sense which you get from the your hand loop. That's magnetic moment. Now a lot of electrons have magnetic moments in this direction. Then there's a bunch, there's one kingdom, there's another kingdom with magnetic moments in this direction, another kingdom with magnetic moments in this direction, okay. So in a material, when all the kingdoms have magnetic moments in the same direction, this kingdoms is what we call as domains, then that whole thing has a magnetic moment in one direction. It behaves so it responds to magnetic field, okay. So I don't have time to go into the details. You should totally download our app, and I've done this chapter of magnetism, and we've gone into a lot of details. A lot of beautiful animations and everything is done, from where does the magnetism of a magnet comes, and a lot of small details about this chapter. So today's session was most like an overview of what this chapter was about, a thumbs up about what all things you need to know. And in regards to how important this chapter is, I would say that you would never find an exam in India happening where at least one question from this chapter doesn't appear. So they always ask a question, and our questions are easy actually for most of the exams. And if you have a passage kind of question in IIT in the JEE paper, it might be a little tricky, but it's definitely interesting, okay. So let me see if I have any questions from you guys. Okay, so Kalash Changal is asking, how are magnetism, electrodynamics and electrostatics interrelated? So I told this to you already, because the source of all these things, electrostatics and magnetism, is the charge, right? And that's why they're related to each other. How they are related is something we need to explore. It's definitely a good question. So I see that I've got only one question today. That's cool. I hope this session was helpful to you. You learned a little bit more about magnets, and I would suggest that you solve all the problems. If you're using our app, all the problems from our all the practice problems from our app. There's this, the good thing about magnetism is, once you learn these concepts, you don't forget. There are some chapters in physics which are very volatile. Magnetism is not one of them, in my opinion. But you do need to practice a lot of questions, because concepts are very less. There's not a lot of concepts, so you can totally nail a question which you get in your exam paper. Okay. Now please download our app. I've told that already, and please go through our YouTube channel, subscribe, find out all the videos that we upload. We use a bunch of really good animation and creative ways to teach concepts. All right, and with that I conclude today's FB Live, and all the best.